Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the optics, and in the section on diffraction we will have the following as the contents for this lecture. They are diffraction at a circular edge, diffraction at a straight edge, intensity inside the geometrical shadow, and lastly diffraction due to a narrow slit. I told you in the previous lecture, when light is traversing through a circular hole or a circular aperture, you do not get a finite point with a particular intensity, because light travels in the form of waves. They undergo diffraction and you get a diffraction pattern, and as I told you in the last lecture, this diffraction pattern was satisfactorily explained by Fresnel by introducing what are called half period zones. I told you how to find the intensity at a given point P. You know the intensity at different points will be different, right? Here the intensity here is you have a bright dot, then you have got darker region. Therefore, we will find the intensity at a point P, then we will try to find the intensity at a point P prime and so on. Therefore, on the screen the intensity will not be uniform. To find the intensities at different points, what we did was to divide the wavefront into number of half period zones, and now O is the pole. When we want to find the intensity at the point P, O is the pole. When we go to the point P prime, some other point, this I will call as O prime, that will become pole and so on, which I will show you later. As I told you just now, if you have got only one half period zone, that is light coming through the first half period zone alone will be allowed to pass through the circular aperture, or in other words, the size of the aperture is such that it allows the light to pass through only the first half period zone. The amplitude will be m1, the intensity will be m1 square. On the other hand, if the aperture or hole is such that it allows 2 half period zones, then the displacement will be m1 minus m2. As I told you in the last lectures, if the amplitude for the light passing through the first half period zone is plus m1, then the light coming from the second half period zone will be minus m2. Why minus sign comes? Because they are half period zones, that is the time difference between the lights coming from the first and second zones will differ by a time interval t by 2, it is a half period, or a path difference lambda by 2, or a phase difference pi. A phase difference pi means what? If a crust is coming through the first half period zone, a trough will be coming from the second half period zone. You know when you are talking about constructive and destructive interferences, a crust and trough will oppose each other. That is the reason why I put M1 minus M2. M1 will be positive, it will displace the ether particle which is assumed to be present in the whole of the universe according to those who propose the wave theory of light. The ether particle will be displaced upward by the light coming from the first zone, whereas the light coming from the second zone will try to pull it down. Therefore, the resultant will be M1 minus M2. On the other hand, if the aperture size is such that it will allow light to pass through 3 off period zones. So, you will have M1, M2 and M3. The resultant will be M1 minus M2 plus M3. 4 off period zones means what will be the resultant displacement? It will be M1 minus M2 plus M3 minus M4, right, 4 off period zones. So, the successive zones will try to destroy each other, whereas alternate zones 1 and 3, M1 plus M3, that is what I am having is M1 plus M3. So, if M1 plus M3 means the intensity will be maximum, you have to take the resultant displacement, square that. So, what is intensity? Intensity is the square of the displacement. You take the resultant displacement and square it. Now, therefore, here you have got M1 and M3 to be added to each other. Therefore, the resultant will be maximum, whereas here M1 minus M2, M1 will be like this, M2 will be like this. So, it will be a minimum. If the hole is such that it allows light to pass through 2 off period zones, it will lead to a minimum intensity, whereas if the dimension of the hole or the aperture is such that it is equivalent to 3 off period zones, then the displacement will be M1 minus M2 plus M3, that will be maximum, giving rise to maximum intensity. Therefore, depending upon the point P, the point P is the central point, depending upon the distance that separates the wave front or the aperture and the screen, depending upon the distance between these two, again depending upon the number of zones, odd zone or even zone, 2 zones will give rise to minimum, 3 will give rise to maximum. Therefore, by continuously altering the distance B, that is the distance between the wave front or the aperture and the screen, the point P becomes alternately bright and dark. That is important. The point, what you get at the point P, it may be bright or dark. It depends upon how many zones are there corresponding to your aperture. So, that can be altered. P, the distance P can be altered, so that the aperture that you got here, light can pass through 2 off period zones, means M1 minus M2. The P will be dark, the intensity will be minimum. On the other hand, if it allows light to pass through 3 off period zones, or light through the first, second, third zones are allowed to pass through, then M1 minus M2 plus M3, that the resultant intensity will be maximum. So, P will be bright. So, P may be bright or dark depending upon the number of zones, either odd number of zones or even number of zones are present or able to light through even number or odd number of zones are allowed to pass through the aperture. Depending upon that, therefore, let me read again. Thus, by continuously altering B is the distance between the wave front or the aperture and the screen, the point P becomes bright or dark depending on whether odd or even number of zones are exposed by the aperture. Okay, that is important. Now, let us go to the point P prime. As I told you earlier, we considered the intensity at a point P. Then we go to a point P prime on the screen, which is far away from P, and at P prime what happens? And there are some interesting things. Now, let us now consider a point P prime on the screen. Let S to P prime be joined. Obviously, you have to S to P prime, the source S is here, P prime, you join that. Then this point I will call as O prime. I will show in the diagram to come. this O prime will become the pole. Now, O was the pole earlier for the point P. For the point P prime, O prime will be the pole, and with P prime as the point, we will be constructing what? We have to construct again off period zones. With P prime as center, we have to construct the off period zone, because we want to find the intensity at the point P prime. The work done by Fresnel should be, the beautiful work should be appreciated. It is a fact that the intensity that you get on the screen when light is passing through aperture, it is not constant. If you would have considered the Newton's ray concept, then for a bright light coming from a torch or from any source passing through a hole, if light is passing in a straight line, then you will be getting a point. For a point source, you will be getting a point image. You do not get a point image, you get circular rings, and again rings with varying intensities and so on. Now, these patterns that you get on the screen can be explained only on the basis of diffraction, and intensity variations can be explained again only by constructing what are called half period zones with either P as the center. Now, we are having P prime at the point where the intensity is to be obtained. So, with P prime at the center, you have to draw again the spheres with differing radii and construct half period zones. We will come to that. And so, P prime is the point we are talking about now. The line SP prime means the wavefront at O prime. As I told you, O prime is the pole. I will show the O prime is the pole, right. Earlier O, this O was here, the pole for the point P. For the point P prime, O prime is the pole. Okay. Now, when light is coming, the interesting point, as I told you, when light is coming, the wavefront is coming here. Now, you know, you look at the slit here, right. The aperture is here. What is this is aperture, right? What is aperture? Aperture is nothing but a hole. You see the hole here. AB is the diameter of the hole. You should understand what I mean by aperture. Aperture is a small hole in 2 dimension. AB is the diameter of the hole. So, light should be passing through this hole. Now, if light is traveling in this direction from S to O prime to P prime, then your hole is here, right, but light is traveling this direction. Now, what if you have the O prime of the pole, from O prime to A, what will happen? You look at this region O prime to A, what will happen? The light is obstructed by the slit. I hope you understand the point. This is a material, it may be cardboard or a metal plate. You are drilling a hole here, this is the hole, okay, the aperture. You have got the material medium, which is opaque, the medium, right. It may be a metal plate or a cardboard. You have a hole here, this is your aperture. Light cannot pass through the opaque substance, right. So, you have got O prime as the pole. Now, I will ask the question, what will happen to the light that is found in the region O prime to A? O prime to A, that light is obstructed by the opaque slit. That is the important point. So, if you have got, I am going to construct off period zones with O prime as the center, you will have the first off period zone. Only some of the off period zones, maybe 2 off period zones, you have got the first off period zone with this, the diameter, right. You have got you have this circular off period zone. The second off period zone, if 2 off period zones are cut by your opaque material that you have got here, then the light will be coming to the point P prime because of the light coming from the 3rd, 4th and 5th half period zones. This point should be borne in mind. I hope you understand. The point is the following. If with respect to O prime, light is incident here, when you are constructing off period zones, the light which is passing through the first half period zones will obviously cut, because the off period zone is here. The obstacle comes up to the point A. So, some of the off period zones will be cut because O prime is above O from center, and light will be obstructed by the region O prime to A. Okay, that is important point, that I will come to that. So, the point is the upper half of the wavefront is cut off by the obstacle. This is what I was trying to tell you. The upper half of the wavefront is cut off by the obstacle. the upper half of the wavefront is you have the region here that will be cut off by the obstacle. The light being cut by the material that you have got here, as far as the point O prime is concerned, this O prime A, the light from O prime to A will be cut off because it is obstructed by the material that you have got here. So, a few half period zones will be cut. So, the first two zones, let us assume the first two zones are cut off by the obstacle, then the light will be coming from the third, fourth and fifth zones only. Hope you understand that this region O prime to A, it cuts the light passing through the first two off period zones, because this is an opaque material, right. So, with respect to O prime, you draw the first zone, the second zone, the third zone will be here, the third zone light will be coming here, right. The fourth zone light will be coming. The first two zones are cut off. So, if the first two zones are cut off by the obstacle between the points O prime and A, and if only the third and fourth, fifth zones are affected by the aperture, exposed by the aperture AOB, then intensity at P prime will be maximum. That means, light will be coming from third, fourth, fifth and other zones. Thus, if odd number of off period zones are exposed, the point P prime will be having maximum intensity, and if even number of zones are exposed, point P prime will be of minimum intensity. So, the point is, with respect to the point P prime, some of the zones, especially the first few off period zones will be cut off, light coming from the other half period zones will come, their effect will be felt, and depending upon the number of zones, whether it is an even number, odd number, the intensity will be either be maximum or minimum. As the distance of P prime from P increases, I told you this, I asked this question earlier also. When you have the first zone here, you got a plane wavefront, you divide this is the first half period zone, second and third, whether the displacement which is caused by the light coming from the first, second, third, all of them will be equal? They will not be equal. We have been discussing for a long time the obliquity factor. I told you in the last lecture also, if the displacements caused are M1, M2, M3, M4, etc., due to the light passing through the first, second, third, fourth zones, etc., then M1 will be greater than M2, M2 greater than M3, M3 greater than M4, because as the angle increases, otherwise the so called obliquity factor, the angle made by the higher zones will give rise to lesser displacement. That is the point I am trying to emphasize here, as the distance of P prime is a point which is found farther away. If P prime is somewhere here, suppose not here, okay, it goes somewhere here, then the angle subtended by P prime with respect to S will be very large, with the half period zones will be large. Therefore, because of obliquity factor, the displacement cost will be due to higher zones will be lesser, as I told you, M1 greater than M2 greater than M3, and so the by M infinity, that zone, the displacement cost will be almost 0. Infinity minus 1 will be greater than M infinity. So, in the first two zones are cut off, as I told you, what will happen? Now, as the distance increases, the intensity will gradually start decreasing because of the obliquity factor. It is because with the point P prime far removed from P, the most effective central off period zones are cut off by the obstacle from O prime to A. With the outer zones, the obliquity increases, the angle subtended increases with reference to the point P prime. Hence, the intensity of maxima and minima will also be less. If the point P prime happens to be of maximum intensity, then all the points lying on a circle of radius PP prime on the screen will also be maximum intensity, something like Newton's rings. If a particular point is intense, then all the points with the same radii of the radius will be having similar intensity. Thus, with a circular aperture, the diffraction pattern will be concentric bright and dark rings with the center P bright or dark depending on the distance b. I told you the point P itself will be bright or dark depending upon the fact whether you have the aperture equivalent to odd number of zones or even number of zones. The width of the rings continuously decreases. I will show the picture where you will see the width of the rings continuously decreases. You have the, you see the rings coming closer to each other, right? You got a ring here, okay, you have got a ring, the rings, this is what I am trying to, the frontal diffraction of a circular aperture, the width of the rings continuously decreases. So, we have been discussing so far the phenomenon of diffraction due to a circular aperture. Now, we will pass on to what happens when a light beam is intercepted by a circular disc. In the path of the light beam, you have a hole, I am going to place a disc. When you place a disc, then again if you look at the Newton's theory, you should have a dark region on the screen, but you are not getting a dark region, you get again rings. Thereby you feel that the ray concept is wrong, you have to make use of the phenomenon of diffraction. The light beam bends around the circular disc, that is obstacle. So, you have got a opaque circular disc. You have got a, what I am doing is, I have got a source here, okay. This is the obstacle. You have the object which casts a circular shadow. We saw the formation of shadows earlier, but you do not get a simple shadow, but you get rings here, right. The fact is, the rings that you observe, the diffraction patterns were observed first by Grimaldi, the Italian physicist. Now, therefore, if you have an obstacle, there is an obstacle here, there is a point source, you got a point light source, okay. The object which casts circular shadow, okay. The screen with the shadow of circular object, the Poisson spot. Anyway, the point is the following: you do not get for a point source, for a obstacle such as a circular disc, you do not get simply dark region, but apart from dark region, you get rings. These rings can be explained only on the basis of the phenomenon of diffraction, or in other words, I will tell you the pattern that you get will look like this, okay. The diffraction pattern that you get, in what case? You have got a source of light, okay. You have an obstacle here, CD is the obstacle. See, you do not think CD is a lens, it is an obstacle, it is an opaque obstacle, right. Opaque disc that is kept in the path of the light beam. This is a geometric shadow, right. What I want to know is, in the shadow region, I get this kind of rings, right. So, light is bending and it is coming in the shadow, in spite of the fact that the geometric shadow, you get rings here. The formation of rings can be explained only on the basis of the fact that light travels in the form of waves. So, S is a point source of monochromatic light. Then you have here CD is a opaque disc, CD is a disc here, P is the point on the screen such that SAP is perpendicular to the screen. The screen is perpendicular to the plane of the paper. XY is the incident spherical wavefront, EF is the geometrical shadow. So, let us be now concerned only these two things. XY is the wavefront, we have to see the diagram where is the wavefront, and secondly the geometrical shadow region. So, this is the wavefront, XY is the wavefront, this is the EF is the geometrical shadow, and we observe within the geometrical shadow this kind of pattern. So, this is the wavefront. So, to explain the wavefront, to explain the formation of these rings, once again you have to draw the half period zones. So, with respect to the point P, then once again the wavefront is divided into number of half period zones, taking the center of the disc as the pole. Center of the disc is taken, the point A is taken as a pole, with P as the center, draw half period zones, spheres, they will give rise to half period zones on the wavefront, and because of the half period zones, the resultant displacement, what will happen? As I told you, two things ought to be kept in mind: the displacements caused by the light coming through the first, second, third off period zones, whether the even number, odd number. The second point is, I told you M1 will be greater than M2, M2 will be greater than M3 and so on, the so called obliquity factor. So, let us concentrate now on the second paragraph, which says that if one half period zone can be constructed on the surface of the disk, supposing you are obstructing, suppose a disk is able to obstruct one half period zone, then the light will be coming from the rest of the other zones, rest of the half period zones. That means the second, M2, M3, M4. So, what I do is I write the resultant M2 minus M3 plus M4 minus M4, M5 and so on. Okay, that is obvious. Because the obstruction is such that it is able to obstruct light coming from the first half period zone. So, M1 is 0, because M1 is, light is not passing through the first half period zone, is cut off by the obstacle. The size of the obstacle is such that it cuts the first half period zone. Then the light will be coming from the second, third, fourth and fifth zones. Light coming from second will be opposed by the third. The opposite, the successive zones will oppose each other. So, M2 minus M3, then again plus M4 minus M5. The second point is M2 should be greater than M3, should be greater than M4 and so on. Then this summation, you all know by now, should be equal to M2 square by 2, M2 as M2 by 2 plus M2 by 2 minus M3 by 2, and you can cancel the bracketed terms. These things we have seen earlier. Thereby, we assume this whole thing will be resulting in M2 square by 2, and therefore, you have, supposing first two zones are cut, then the resultant will be, instead of M2 by 2, it will be M3 by 2. So, the intensities caused on the screen will depend upon how many off period zones are cut by the circular disk. This is what you are having here. So, let me now summarize as to what we have seen in the present lecture. Diffraction due to circular aperture will lead to alternate bright and dark rings. The diffracted intensity depends upon the fact whether you have even or odd number of zones. The obliquity factor should also be taken into account. The diffraction pattern due to a circular disk will also give rise to bright and dark rings. We will now pass on to the question session. The questions are: how will you explain the diffraction at the following cases? A. Circular aperture. B. Circular opaque disk. C. Comment on the obliquity factor. With this, we come to the end of this lecture, and we will see the diffraction phenomena in certain other cases in the lectures to come. Thank you.